Welcome back to part 7 on transformations of functions. We are going to start looking at horizontal stretch and shrink. Another way of saying that is compression and expansion. It depends on who you're talking to or who your instructor is. So today we're going to look specifically at a function that has a maximum right around 221. And I want to show you what happens if you scale this graph or this function by either a number greater than 1 or less than 1. Let's take a look at f of x equals x to the third minus 6x squared minus 45x plus 162. The graph on the right shows the function f of 3x. Notice that the 3 is substituted inside the function. Where the graph intersects the x-axis in the left graph and the intersections with the x-axis on the graph to the right have a relationship. And this is what we need to talk about first. Compare the locations of the x-intercepts on the two graphs. The left graph has intercepts at -6, 3, and 9. If we look at the right graph, it has intercepts at -2, 1, and 3. Now, we need to figure out what happened to the values of each intercept because it directly relates to f of 3x. Well, if we look at -6, 3, and 9, we can find the numbers in the second graph by dividing by 3. So let's say we have 3x equals -6. We can take the 3 away from the x by dividing both sides by 3, and we will get -2. So in effect, we have 3x equals -6, 3x equals 3, and 3x equals 9. If we solve each one of these for x, we get x equals -2, x equals 1, and x equals 3. Now that's an interesting relationship. When you think of how a graph is either compressing or expanding based on a new substitution, you can think of 3x as solving for a 0 of the polynomial by dividing the 3 away from the x. Now, it might be helpful to see an actual graph of these because you might be thinking, well, wait, if I put a 3 in front of the x, it should make the graph taller. And remember, if you substitute a number outside the function, like if we were to put a 3x in front of the whole function f of x, that is what would happen. It would get taller. It would stretch vertically. But we are substituting the value inside the function. And so it's going to change the function in a horizontal manner, not a vertical manner. Take a look at the function right here, where it shows a cubic, just like what was on the handout. And we can see that right now I've also inserted a scalar a wherever there was an x in the original function. Now I can see what will happen as a changes values. If I push play, I can see that as a increases, the function compresses, and it continues to compress. I have it scaled from 0 to 10. And then as it gets closer and closer to 1, you can see it expand. And now I'm going to pause it. Notice that a got less than 1 but greater than 0. It starts expanding past the original x-intercepts. This is very important for the next question we'll look at. But at the same time, it's also important to notice that as a equals 1, the graphs are identical, and as a gets bigger than 1, the graph compresses and the intercepts are smaller values. Compare the locations of the x-intercepts on the two graphs. On the left, we have -4, -1, and 3. On the right graph, we have -12, -3, and +9. If we look at what happened to the values of each intercept, to get from -4 to -12, we would have to multiply by 3. To get from -1 to -3, again, we would have to multiply by 3. And to get from 3 to 9, we would have to multiply by 3 again. Hopefully there's a pattern that you're seeing. G of 1/3 x is the graph on the right. Again, the height of the graph has not changed at all, but the x-intercepts have been scaled. If we set 1/3 x equal to -4, we can see that x, when we solve for it, will be -12. Similarly, if we have 1/3 x equals -1, solving for x will give us x equals -3. And lastly, 1/3 x equals 3. Solving for x will give us x equals 9. And there we have it, all three intercepts of our new polynomial g of 1/3 x. So when we have a fraction as a scalar inside the function, it multiplies the original x-intercepts. So to recap, the y-coordinates of y equals f of cx at x is the same as the y-coordinates of y equals f of x at cx. So the x-coordinates in the graph of y equals f of x correspond to the x-coordinates in the graph of y equals f of cx, multiplied by 1/c. If you want a function to horizontally shrink, c must be greater than 1, and if you want the function to horizontally stretch, c must be between 0 and 1. If c is greater than 1, shrink the graph of f of x horizontally by a factor of 1/c. And if c is between 0 and 1, stretch the graph of f of x horizontally by a factor of c.